thanks very much to the organizers. You're taking really good care of us. And thanks also for scheduling me right after Sasha's talk. That was convenient. And especially thanks to Sasha for advertising my talk so that you know, stayed awake and made it to it. I hope I stay awake. I've had a little too little sleep, a little too much jet lag, but a lot of coffee to compensate. So hopefully I'll keep my wits about me. So I'm talking about Khovanov-Lauda or Khovanov-Lauda-Ruquier algebras, and really a lot about their simple modules. Okay, and this is available on the archive. So let's see. So another name you might hear is Quiver-Hecke algebras attached to these. And so, as we've heard today, they depend on a symmetrizable Cartan datum. And so I, indexing my simple roots, my Cartan matrix given by pairing simple co-roots and simple roots. I'll use angle brackets for that form and round brackets, parentheses for the symmetric pairing. And of course, there's a Kac-Moody algebra G attached to this. And these were developed, well, in order to categorify, well, hopefully UQG, but let's just say UQ minus G, half of the quantum group. And what does it mean to categorify? We've heard a bit about this. We really want to find, for instance, some category whose Grothendieck group realizes, for instance, UQ minus, or its modules, or something. Okay, and what goes inside the question mark? Well, these were these algebras that they invented. Okay, so and Khovanov and Lauda showed that if we take A to be Z adjoint QQ inverse, that is A by algebras, the Grothendieck group of, for these algebras are their projective modules, if we take that Grothendieck group, it is isomorphic to UQ minus G, the integral form of it. So there's still many goals left that, as a community, of course, we'd like to achieve is categorifying all of UQ, G, not just UQ minus. And as Sasha mentioned, Ruquier has announced progress towards this in all types. Yeah. Another goal would be to categorify highest weight representations of UQG. Another goal that we're working towards is, well, I haven't really said what these algebras are, but we know they have these cyclotomic quotients, these finite dimensional quotients, and we want to understand those finite dimensional quotients. And then, of course, we want to tie these two goals together, because the hope is that, in fact, the Grothendieck groups of these cyclotomic quotients will categorify this highest weight module, and it will do it on the level of the integral forms as well, not just over the field. Okay? And we want that to hold as UQG modules, well, or the integral form. Okay? Just as Ariki did, say, for cyclotomic Hecke algebras, he was working with projectives, Granovsky worked with simples, and also got this result. And in type A, as we just heard, this has been done by Brendan and Klestjev. So what are the results I'm going to speak about today, or give you some ideas towards their proofs, is that, in fact, if we do take these cyclotomic quotients, yet to be defined, and look at the Grothendieck group, whose basis we're taking to be isomorphism classes of simple modules up to grading shift, we do get the integral form of the highest weight representation, but not as UQG modules, only as UQG plus modules. So we have an action of the e's on both sides. That's compatible. We don't have the whole quantum group acting. So of these goals, we sort of have half of that. Okay. Another result that we do have, though, is that if we form a crystal whose nodes are the simple modules of the cyclotomic Khovanov-Lauda algebras, then we get the crystal of V lambda, so-called B lambda. Okay, so we get a highest weight crystal structure on the simples. Even if we don't have the whole quantum group acting, we can still understand crystals abstractly. Okay. And of course, if we move away from the cyclotomic quotients, we go back to the original algebras, R, if we do the same with them, the crystal structure on their simple modules is the crystal B infinity, which is the crystal we associate to UQ minus. Okay, or we could flip it upside down and think of it as the crystal for UQ plus, if you're more comfortable with that. Okay? So did I say this was all joint with Aaron Lauda? If I didn't, I meant to. And I should say I'm kind of hopeless about like literature and referencing. So if I leave out crediting people, feel free to say such and such did that. It's definitely not a purposeful omission. Okay. Luckily, in Sasha's talk, he mentioned a lot of what everyone's done. So you already know who's responsible for what. Okay. So this crystal structure, where does it come from? Well, we have crystal operators. And the crystal operators are EI twiddle, or EI tilde, is basically socle of I restriction, or an analog of what we mean by I restriction. And Fi twiddle is cosocle of I induction. And you might have heard words top or head for cosocle. I like cosocle because it's the it's the largest semisimple quotient, whereas the socle is the largest semisimple sub. So I like to say socle, cosocle. Okay? And so these ideas of these crystal operators, what we study about them, how we extract information, it very much follows the work of Granovsky and his 99 archive preprint. Okay? And so today what I'm going to talk about is, towards the proof of statement 3, some of the ingredients that we use that don't just cookie cutter follow Granovsky. So a lot of that paper just really repeats what he did, as verbatim as possible even. But there were certain things that you had to actually think about a little bit and do a little extra work on, and I'm going to be talking about that. We're going to have to get our hands a little dirty with generators and relations and simple modules to do that. Okay. Oh, and I should say, so I'm only going to talk about some of the ingredients that go into statement 3, but once we have statement 3, once we've recognized the crystal B infinity, getting to statement 2, going to the highest weight crystal, going to cyclotomic quotients, isn't very hard because we know how B lambda embeds in B infinity and how to recognize it. And you can say it inherits a crystal structure from that. So that does our work for us. And in fact, once we have statement 2, if we combine it with work that Khovanov and Lauda already did, 1 falls out, being a little bit careful about the integral forms. Okay, so now some definitions, and this is just god-awful slide. It's really messy. I wrote it at like 4 in the morning. I apologize, but it actually fits very well that it's such a messy slide and that we're talking about generators and relations, because I don't really want you to be reading about generators and relations and thinking about this. It's just to give you a bit of a flavor. So for instance, if we were starting out, say, with the affine symmetric group, which actually we heard a little bit about this morning, we can think of it as the semi-direct product of the finite symmetric group and a lattice z to the m. So we have generators, the SIs, and we have more generators I'll get to. And of course, these satisfy the Braid relations. These are sort of my quadratic Braid relations and my so-called cubic Braid relation that we all know and love. And of course, my quadratic relation is that these are simple transpositions. They square to the identity. Nothing new there. And then the affine part of it, the z to the m part, is that we have these x's. And we think of xr as sort of your standard basis vector, 0, 0, 0, 0, 1 in the rth place. And so, of course, they commute with each other. These give me that's an n. That should be an m. They give me the z to the m part. And of course, SR x sub t equals x sub s sub r of t SR. In other words, an SR moves past an xt at the expense of permuting around where this 1 goes. All right, so that's not at all a surprise. We could compare that, for instance, to the relations for the degenerate affine Hecke algebra. I almost always never go degenerate. I'm a very affine Hecke algebra non-degenerate kind of person. I think it's kind of funny that Sasha had the affine Hecke algebra in his talk and I have the degenerate in mine. because I never do that, but it was useful to see how the relations match up with the Khovanov-Lauda algebras. So here we still have generators S sub r. They have the Braid and the quadratic relations is over here. We also have XRs that commute. But now this relation of how x's and s's move past each other is slightly deformed. That an SR x sub t minus x sub s sub r of t of r gives me not always 0. Sometimes it can give me 1 or negative 1. It gives me 1 or negative 1 when the x I'm putting in here is x sub r or x sub r plus 1. Okay, the only time you're actually non-trivially moving this where this 1 is around in this relation. Okay, and I'll mention that we can actually, if we don't like having this 1 there, if we really want to recover a nice intertwining relation like this, there are intertwiners in the Hecke algebra, the affine Hecke algebra or degenerate affine Hecke algebra. There's a formula for them, and they do have this nice, these should be uppercase x's, sorry. They do have this nice intertwining relation. They satisfy the Braid relation. The quadratic relation on them is a little bit weird. You square them, you get a polynomial in x's. Okay, but it's worth thinking about intertwiners because we really care when we study the simple modules here. One way that we attack them is we look at the weight spaces as far as how the x's are acting, the simultaneous generalized eigenspaces of the x's. And so if you're going to study a simple module based on that, you want to know how your other generators interact. And so if you have intertwiners, they take you from weight spaces to weight spaces. And that's an important way of looking at them because, of course, as we saw, we're going to actually be projecting to weight spaces quite a bit when we're studying these new algebras. Okay? Now, could you do the lights? So I actually originally crammed it on this slide, the relations for the Khovanov-Lauda algebras, which are very similar to the relations that Ruquier has, but his are slightly more general. And you can see it's just a mess. And so I also wrote it on the chalkboard. But the salient features to take out is that we have these new generators. Okay? So let's see, what's my data? So a little different from Sasha. I'm calling these r sub nu instead of, what did you do with alpha? So nu, I'm writing it, I could have written it as a sum of m sub I alpha I. But for whatever reason, the notation that they used and then we repeated, we replace alpha I with just I. So we say m sub I. So we're working in, we're working in the natural numbers adjoin I is where we're thinking of our nu as living, but really we want to think of it as in something in Q plus, okay, in this positive cone. The size of nu is m if I have m many simple roots I'm summing over. Okay, we say that an m tuple from I is in seq nu, as in sequences of nu. This is what Sasha had called I super alpha, which I agree is a nicer notation. If nu is the sum of the support in here, okay, and so what we have that's sort of new in terms of generators in this algebra are these orthogonal idempotents, and instead of calling them E of I, we call them 1 sub I. So you could say E of I or 1 sub I, same thing. It's easy to remember it's an idempotent based on that. So there are these orthogonal idempotents. We have psi sub r's instead of s sub r's. And they satisfy, let's see, maybe I'll, refer to the chalkboard. They commute if they're far apart. Okay, that's nice. But our cubic Braid relation suddenly becomes kind of ugly. Okay? Our 3-term Braid relation, it's no longer true that if you look at the difference between psi r plus 1 psi r, and psi r plus 1 psi r plus 1, that you get 0. So after having projected to a weight space, it's possible in some very special cases that we get some sort of polynomial in the x's. Okay? And I call my polynomial part x's. They commute with each other instead of y's. We had y's in Sasha's presentation. That's not hard to remember. Okay? So that's a difference. Another difference is for our quadratic relation. Okay? It's not too bad. Our quadratic relation, if we multiply a psi by a psi, we might get 0, we might get 1, or we might get some sort of polynomial in x's. Okay? And that may be you should maybe think of how when you squared intertwiners, you got something involving x's. Maybe that's sort of a motivation, a feel for where this is coming from. Okay? And how are x's moving past size? Well, actually, that feels very much like the relation in the degenerate affine Hecke algebra. That sometimes you can get sort of 1 minus 1 or 0, but now it's this idempotent, 1 sub I minus 1 sub I or 0. Anyhow, you can forget those relations now. I don't know if they made anybody happy or unhappy, but I'm going to keep that slide. Oh, I don't need to keep the slide out to the side because it's on the board. Hopefully, if I get time and actually do some of the proofs I have in mind, they should bring the relations to life, okay, later on. And what time do I end at? I started at 4, is that right? Okay, great. All right. So when Khovanov and Lauda were developing these algebras, they were really very picture-based. So they have like strong topological backgrounds that they're working in. And so all the relations up on the board, they were actually drawing these pictures, these crossings that were labeled by i's and j's and so on. And these dots are like x's or x1 squared. Yeah, question? Oh, yeah. Thank you. Can we turn the lights back down? Sorry. OK. So these pictures here are really incorporating all of these algebraic relations written down on the board. So whenever I talk with Aaron, he always is like, let me think in pictures. And I'm always like, give me an algebraic formula. So it works pretty well. So let's see. For instance, you know, this picture here is sort of telling you how size and x's relate to each other. And in fact, it's we're in the 0 case, the else, that an x and a psi are moving past each other, and so on and so forth. So this relation here is really captures the cubic Braid relation, that you get some extra garbage, this sum, but you know, sometimes that sum isn't there. So anyhow, I'm not the expert with pictures. I copied this off of one of Aaron's slides. But one of the great things about this being picture motivated is that I think for them, this is a lot where this notion of degree came from. That degree was much more natural, and the grading was more natural and more transparent to them when they were thinking in terms of pictures. So it's worthwhile to understand what these pictures were and where they were coming from, even though I don't. Whenever we have to do things with grading, I always say, Aaron, you know, you have to do it. But the grading that they put on these pictures, the degree, one thing I'll note, one thing that I like about it, is that it's compatible with the so-called quantum shuffle. So if we have a word in the i's, so what I think of a shuffle, you know, if you're going to shuffle some cards, what do? You take your deck, and you interlace them. And they could happen in any of these ways, right, binomial coefficient number of ways. So a shuffle is really just a minimal length left coset representative for a parabolic subgroup inside of Sn. All right? And so what happens if I shuffle these guys past each other? I get the sum over all the different ways of interlacing them. But you want a Q, a quantum shuffle. So depending on what's moving past what, and what these are labeled as I and J strands, you attach some powers of Q to it. And so this formula is just sort of a recursive formula to figure out what the power of Q is. I'm actually not even going to go into what the formula specifically says. You should just know it exists. I think it's Leclerc that came up with it, and it's compatible with our notion of degree. Okay? So the grading is, as we just heard, one of the really wonderful and powerful properties that these algebras have. It's what's bringing something very new and mysterious to the picture, and very useful. For instance, if you want to get a handle on dual canonical bases, you need this Q to be in there. You need this grading and this degree. Okay, and oh look, I remembered to credit some people. It came up in a very key way in the work of Brundon, Klestjev, Ram, Wang, etc. Okay. Now in this talk, though, I'm going to really ignore the grading. All of my maps, my isomorphisms, they'll be homogeneous, but there might be degree shift. So a lot of the things I'm going to say, because I'm talking about simples, I can really think about that the grading isn't there, that it's like q goes to 1. Or maybe a better analogy is saying that I'm really sending the q to 0 since I'm going towards a crystal graph result. Okay? So, right, so everything I'm doing is up to grading shift. And so I'll put a little sort of star in various statements when I'm saying something's true, but I really mean up to grading shift. The star there will just denote that there's a grading shift allowed somewhere. Okay. Save that for later. Okay. So actually, this slide I can go through very quickly because we've already seen some of it, just in different notation. So the identity of my R nu is the sum of these idempotents. Okay, I have my 1 sub i's, where the i's are just sort of rearrangements of the support of nu. So let's see. If you can sort of break apart nu as a sum of mu's, say you have mu1 up through mu k, who sum to nu, then you can talk about a parabolic subalgebra. R sub, I call it mu bar for the tuple. Okay? And R sub mu bar is really, I want to sort of identify it with a subalgebra of R nu in the following way. I really want to think of, I can take R nu sub 1, nu sub 2, up through R nu sub k, sort of tensor them together and realize that as sitting inside of here. Much as we saw in the last talk, I guess it was H sub alpha sitting inside H sub alpha plus alpha I in the same exact way. Okay? We can stick it in there using these idempotents. Okay? But once I do that, once I have these parabolic subalgebras, I can talk about induction and restriction functors between them. Okay? And part of why I can do that is that not R sub nu, but R sub nu hit with this idempotent. That's like you just take the identities from each of the parts of the parabolic. That is a free right R mu bar module. Okay? And its basis corresponds to minimal length left coset representatives of SM in the parabolic that corresponds to mu. So shuffles. All right? And then, so that's free, so that's great, and you just kind of extend by 0 to the rest of R nu. All right? And to lighten notation, when I'm inducing between modules of these parabolic subalgebras up to R nu, if it just understood that the module that I'm putting in is going between R mu bar and R nu, I won't even write any subscripts or superscripts, although maybe I will in a few cases if I want to specify. All right, so let's look at a few examples of some of these R nus and some of their simple modules. All right, so in the case that nu is just I, or alpha I, if you will, all right, so then our ring is R of I. It has so we don't have any size. We just have our x's and our 1 sub I, and that's basically it. All right, so we have a unique simple module. We call it L of I. Okay, sort of following the notation in Sasha's book. And up to my isomorphism grading shift, there's my star. It's the unique simple module. Its dimension is 1. X axis 0 on it. 1 sub I acts as the identity on it. Great. Okay. So there's one of these Khovanov-Lauda algebras. There's all of its simple modules. Let's study the case that nu is m times I, or rather m times alpha I. All right, well, this also has a unique simple module up to grading shift. We call it L of I to the m. Okay, and one way that you could construct or realize L of I to the m is through this induction process. You could take the outer tensor product of all these one-dimensionals, induce up. Okay, there's other ways of constructing it too. It has dimension m factorial. And if we actually took its graded dimension, it would be the quantum version of m factorial. All right? And again, people have their favorite grading shifts. So people don't always like to do this, but this one will be nice and centrally symmetric, as we heard was a good thing to have for your simples. Okay, and this Khovanov-Lauda algebra in this very special case, R of mi, it's basically the same as the nil-Hecke algebra, or affine nil-Hecke algebra, and the grading, the degree put on it is compatible with the grading that you put there. right? And that was some of the motivation for it. Okay, so I claim that knowing this, really understanding this particular case, nu equals mi, is like knowing our SL2 strings. It's like knowing when we just have in a crystal, say, a whole bunch of i's acting all the same I. It's understanding SL2 modules. Okay? And of course, we want to understand all of UQG eventually, but that's a start, the SL2s. Okay? Another thing that we get as a byproduct of understanding this particular case, where nu has all its support at I, is now we can define our crystal operators. So let's let M be a simple R nu module. We'll define the crystal operator EI twiddle acting on M. It's going to be the socle of this so-called I restriction. So what is that? So we restrict M to this parabolic subalgebra nu minus I, if it makes sense, if we can peel an I off. If not, you get 0. That's OK. And then further throw this I away. Restrict down so it is a nu minus I, an R nu minus I module. And then take the largest semi-simple submodule. Sort of dual to that are Fi twiddle of M. You take the cosocle, maximal semi-simple quotient, of induced from the parabolic nu I to nu plus I, and take M and outer tensor it with this one-dimensional simple module, L of I. And by the work of Khovanov-Lauda, following the work set up in Granovsky-Vazirani, Fi twiddle of M will also be simple, and Ei twiddle of M will be simple or possibly 0. You could get 0 here. Okay? And we also, hidden in this, before you take socle, this resulting functor is just what we're calling Ei of M. So we only have Ei's acting. Okay? But that gives us crystal operators Ei twiddle. And we can define Fi twiddles even if we don't have Fi's acting. And we don't have Fi's acting yet. There's ideas for what they should be, but there's nothing proven yet, at least not by us. Okay. All right, so we've got our crystal operators. We'll define the weight of M to be negative nu, if it's an R nu module. We can define epsilon i's in the standard way. How many times can you hit it with an Ei twiddle and not get 0? And we're going to sort of cheat and say phi sub I should be such that phi sub I minus epsilon I gives you the weight, basically. So phi sub I should be epsilon I minus hi paired with nu. And that minus is there because it has weight minus nu. Okay? So actually, already this is enough to define a crystal structure. We have enough data here to define a crystal, and it's actually not too hard to check that all the axioms are satisfied, that abstractly this is a crystal. Okay? Sorry, this is a crystal if we take the simples over all nus running in with support coming from I. All right? But how are we going to actually get that it's B infinity, the crystal that goes with UQ minus? Well, we need many more ingredients. I can't go through them all today. I'll give you some of the highlights, hopefully. So we already said we understood the SL2 strings. We already understood when we kind of restrict to a rank 1 case, these in the case where nu is M times I. Okay? So the next thing is we want to mix up some i's and j's. We want to go to the rank 2 case, little SL3s and G2s and so on sitting inside there. So it means I want to understand the simples of the case when nu is Ci plus Dj for some I and j. Okay? And we might as well assume that when we pair alpha I and alpha j, we get something non-zero. Otherwise, actually, the representation theory is pretty easy. All right? What else do we need to understand? We need to understand a little more than that if we want to get B infinity. For instance, Kashiwara and Saito, I don't know if that's the first place it appeared, but it's the reference that we cite. They characterized B infinity via the existence of strict embeddings from B infinity to B infinity tensor Bi. I'm not going to explain here what this crystal is. If you do know it, you know what I mean. If not, it's just extra information that's very useful, actually, in understanding when you have a crystal, is it B infinity or not? Okay? So how are we going to do that? What are some things that we need to follow Kashiwara-Saito? Well, we need to have these sort of right-left symmetric versions of the Ei twiddles and Fi twiddles and the epsilon I data. So what's this EI twiddle check? Well, instead of restricting and pulling an I off the right, this pulls an I off the left. Okay? So it's like, you know, S1 cross Sn versus Sn cross S1 sitting inside Sn plus 1. So we just take the right-left symmetric version of the I twiddle. Okay? And the same thing for epsilon I check. It's just sort of the right-left symmetric version of it. All right? And we're going to need to understand that when we do an Fi twiddle that's doing something on the right, how is that changing what's going on the left in terms of how are these I's interacting and coming through? Yeah? Yeah. Yeah. We called them, I don't know why we called them check. We just did. But yeah, they're like EI star. It's exactly, yeah, it's exactly referred to. I think there was already a star being used somewhere else. So. Okay. And so it's very natural to want to understand sort of, you know, when you're adding I's to the right, when do they percolate through to the left? Sort of, I guess sort of I said here by analogy, if you do have a highest weight module and you just look at it as a U minus module, well then we know that it's U minus modulo the left ideal generated by Fi, say divided powers taken high enough, given by lambda. All right? And if you really want to understand the right-hand side, you want to know if you take a non-zero V in the right-hand side, when does an Fi kill it? Or in the very special case, suppose V, you get it by hitting, you know, a bunch of Fi's and Fj and a bunch more Fi's acting on what 1 is our highest weight vector here. When do Fi's kill that V? In other words, when do Fi's acting on sort of the left percolate through to the right and end up in this ideal? Okay, or this part of this ideal. Okay, so you can understand why it's something that we need to understand about our modules. So we need to understand the structure of the simple R nu modules. In the case, I'm just going to start with nu is Ci plus j. So I'm just throwing in a single j, and I have a whole bunch of i's. But already there's something there non-trivial to do. Once we understand those simples, by an inductive process, we can understand a lot about if we have an arbitrary number of i's and j's, Ci plus dj, or at least we extract some information. Not as much information as in this case, but enough to do what we want to do. As a consequence, once we understand the structure of these simple modules, it will give us information about how adding i's to the right percolates through and adds i's to the left. Okay? That this ingredient we need to understand that we have a strict embedding. Another consequence of understanding the structure is we'll get a second proof of the fact that the quantum Serre relations hold. We have these EIs and EJs, etc., acting on the Grothendieck group. Khovanov-Lauda showed that they satisfy the Serre relations and basically no smaller relations. That was how they showed that it was categorifying U minus. But we can also get at the fact that the quantum Serre relations hold just by studying the simples, showing that they evaluate to 0 when you evaluate them on simple modules. Okay? So, and you'll just see it just falls right out once you actually say what the simples look like. Okay, so now we're starting to get our hands dirty. Okay, so we call these the structure theorems. So let's C equal m plus n, and suppose that quantity is less than or equal to A. A, I don't know if I said it out loud or not yet. A is hi paired with alpha j. Okay? Which, minus that, thank you. Which we might as well assume is non-zero, or else things become very easy. Okay? So then consider the module that we induce up, that's LIM, that's that unique simple module. Outer tensor product L of j, that's that one-dimensional simple, and then outer tensor product L I to the n. That induced module has a unique simple quotient. So we call it script L I to the m j I to the n. This module has dimension m factorial n factorial, meaning that all of it comes sort of just from here, without the induced, right? This module right here has dimension m factorial, n factorial. I induce up, I go down to the quotient, that's all that survives. All the new stuff I got by inducing got killed. All right? Its graded dimension is actually the quantum versions of m factorial, n factorial. Not only that, it's the unique simple R Ci plus j module with its epsilon I equal to n. So you give me an epsilon I, there's a unique simple module that achieves that. Okay? So that's very rigid structure. That's in the case where C was less than A. What happens when C is greater than A? So let's sort of rewrite things. Let's let C be A plus K because it's greater than A. And then, well, let's use part 1. Let's look at these modules, these script L I to the A minus n j I to the n. So here, this is like the case C equals A. All right, and induce that and tack an Li to the K onto the right. Induce that. That module is irreducible for all K. And up to grading shift, it's the same as if we had put the IKs out to the left instead of the right. So here we're getting this right-left information. Okay? And it is this unique simple module with this prescribed epsilon I. Here it's n plus k. So when I look at the simple modules for these are Ci plus j modules, my possible epsilon i's bounce back, and they can only occur between C and C minus A, which is actually happening upstairs too. Okay? So there's one simple for each epsilon I, and we know exactly what it looks like. Notice that when we take part 2 at k equals 1, because this induced module is irreducible, we know exactly what it looks like. This relation, these divided powers of EIs, EJ, and EIs versus more EIs, EJs, and EIs, it vanishes on that simple module, if we call this module n. All right? But that means that the quantum Serre relations, which is a sum, an alternating sum of terms like this, also vanishes on n. Because, right, this is the support of n, basically. And all the other terms in the quantum Serre relations vanish. So the quantum Serre relations vanish on this n. So they vanish on all simple RCI plus j modules. Well, that means they vanish on the whole Grothendieck group. And then it's not too hard to show that, therefore, they have to vanish on any R nu module, even when nu isn't just Ci plus j. If it's any nu, it's going to vanish. Okay. So, all right. I think I heard today that every talk needs a proof. So we're going to do as much of this proof as we can. So what I like about this proof is these awful relations on the board. It sort of uses them exactly. Okay? What I mean by that is, if I didn't know what these Khovanov-Lauda algebras were, if someone just said, find for me an algebra whose simple modules satisfied the structure theorems, just so that you have one for each epsilon. When you get over the tipping point for the Serre relations, these LIs move past just so, you would reinvent the R nu. I think it would force these relations to happen among these generators. It's easy to say that once, you know, Michael and Aaron already showed me their algebras, but I do believe it. Okay? So, okay, let's try to prove this theorem. All right, so this induced module, let's call it capital M. What does the basis of it look like? Well, luckily, right, I said that these parabolic subalgebras, that if we took the larger algebra R nu, we projected by a particular idempotent, that projected module was free over the parabolic. So I'm going to be able to use that information to find a nice basis. The basis looks like, well, first take a basis for each of these pieces. So these u's run through a basis of Li to the m, so the m factorial of them. V is a basis of Lj. Well, it's one-dimensional. That's easy. And the y is, say, a basis for the Li to the n, so there's n factorial of those. And then out front, take our psi corresponding to a minimal length coset representative. Okay, but we need to fix a particular reduced expression because, of course, we don't have Braid relations holding. We need to pick a fixed reduced expression. We can't just take them willy-nilly and say, well, it doesn't matter because of Braid relations. All right? So that's a basis. And I actually, furthermore, it'd be nice if my reduced expressions sort of, you know, I have these i's and a j and an I, and they're getting moved around. I want to sort of move my j around first to the left as far as possible or the right as far as possible, and then let it move around the i's if it wants. And that's all this says here. Okay? So basically, if I start with the sequence I to the m, j, I to the n, w acts on that, and it moves the j somewhere. Okay? And that's just, let's not worry about that. It's just sort of being technical about understanding how the minimal length coset representatives interact with the sequences. Okay? And now let's let k, capital K, be the span of all these basis vectors above exactly when the length of w is greater than 0. In other words, take everything except for having an identity there. Okay? And I claim that when our C, which is m plus n, is less than or equal to a, this k is a proper submodule of my induced module. Okay? So consequently, it's going to be the unique maximal sub, because all that we're missing are the 1 sub i's times these other vectors that come from the original module that we're inducing up from. And these all generate m. Right? Once you have this in a submodule, you have everything. Okay? And so the quotient m modulo k is our unique simple quotient. It's this L I to the m, j I to the n, and it has to have dimension m factorial, n factorial, because that's all that's left. We killed everything else in k. Okay, so k took everything, all the non-trivial shuffles are in k, and they all hang together when C is less than or equal to a. So how do we do that? We need to get our hands dirty with the generators and relations. But for me, that's when they came to life. Okay? So in fact, it's going to be a little bit easier to first take the case m plus n is actually a plus 1. So in the case where k is actually not a proper submodule. But I can use some of the things that come up in the proof later on. It'll make the logic a little bit easier. So this k is not a proper submodule when you cross the threshold. Okay? So how am I going to show that? Well, we can pick special elements in these building blocks, this Li to the m, Lj, and Li to the n, such that when you hit this u with x sub m minus 1 times, you get something non-zero. Which is special because when you hit it an mth time, that kills the whole module. So these x's are such that any x raised to the mth power on this module Li to the m is 0. But the Jordan block size is sort of just exactly m. So you can pick sort of a co-eigenvector for it. Okay? Do the same with the other module. All right? And, well, so k, right, contained basically anything non-trivial that I put out here. So it contained psi sub m and psi sub m plus 1 times these particular u, v, and y. Okay, and remember, m was exactly where, m plus 1 is exactly where this j occurs. So these are the minimal length coset parameters that first move the j to the left and first move the j to the right. Okay? So if k contains those guys, it contains this sort of cubic braid-looking relation. The difference between psi m plus 1, psi m plus 1, and psi m plus 1, psi m times this u, v, y. Now we get to use our relation that's on the chalkboard, and it said, okay, there were these cases. You know, you blah, 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 if this, this, and this. But believe me, we're in case 1. Okay? In case 1 said we got some weird polynomial in the x's. And what did we get? We got a sum over k from 0 to a minus 1, x sub m to the power a minus 1 minus k, times x sub m plus 2 to the power k, times my guy, u tensor v tensor y. And these guys sort of live in the parabolic subalgebra I'm tensoring over, so they can move past the tensor. When they do, this xm comes and it attacks the u. Okay? This xm plus 2 moves over into this guy and it attacks the y, but it sort of becomes the x1 in the notation that if I think of L I to the n, you know, re-number starting at 1, 2, 3 up to n. Okay? And this guy, if k is too big, this guy's always 0. If k is actually greater than or equal to n, this guy's always 0. If this exponent is greater than or equal to m, this guy is 0, which basically means you do your algebra, k is less than or equal to n minus 2, that means the only time that this doesn't contribute 0, 0, 0, 0, 0 is exactly when k is n minus 1, in which case we get the u prime here and the y prime there that we chose up above, but that are non-zero. So my module k, my purported submodule k, contains this 1 sub I u prime v y prime. Well, if we were taking the submodule generated by it, we'd get all of m. As soon as you get a 1 in there, you get all of m. Okay? So this actually showed that just when we went over the threshold, we didn't have a proper submodule. Okay? But if, in fact, we go back to, well, let's go back to m plus n less than or equal to a. If we redo that same proof, those exponents that I had, the k and the a minus 1 minus k, they're always too big. Right? We had this very tight threshold that they just exactly were both non-zero at the same time. And now that's because m plus n was exactly a plus 1. If we're anything smaller than that, the exponents are always too big. You always get 0. So we always get an honest Braid relation holding. All right? So that's good because it means that, that you're not going to pop outside of k. Right? You could imagine when you look at these relations on the chalkboard, you have things with size that have non-zero length. When you hit them with x's or other size, you get terms involving things of smaller length. And maybe you could pop outside of k. We're showing this doesn't happen. Okay? Also, if we take the other Braid relation, we also get the honest Braid relation showing. And that's because in these two cases, we actually fell into this case, the 0 case. We're in the else case there. So that's the easy case that we get the honest Braid relation holding. And this honest Braid relation, it actually does decrease length, but only by 1. Because it falls into the parabolic subalgebra. So we're good, all right? And then, all right, so as I said, this cubic relation could have decreased length by 2 of the elements in my capital K, but they don't, okay? So then I just have to look at my other relations that decrease length. If I have a psi m and a psi m times, say, a UR tensor V tensor Y sub S, well, then I go into my other relation. Okay, my other relation says, well, I get some funky polynomial in the x's. And let's look at what happens. This x sub m to the a passes under the tensor and attacks the u. Well, a is certainly bigger than m, so this gets killed. This x sub m plus 1 is raised to some power that we're assuming is non-zero. And so this guy was only one-dimensional. It was always killed by the x's. So this guy goes away at 0. I get 0. And so that means that, OK, getting 0 is fine. I don't pop out of k. I don't get decreasing length at all. K was everything except for like the 1 tensor u's and v's and y's. OK? And what happens if I move an x past? That's even lovelier because we never fall into, you could imagine we could fall into these cases like in the degenerate affine Heck algebra, but we don't. We always fall into the 0 case. So we also never decrease length. And that's because of the structure of this I to the m, j, I to the n. It just doesn't happen. OK? But we sort of, to get that, we really used every relation. And we just really used it on the nose. OK? So, oh, yay. That was the end of my proof. And so that's a good place to end the talk and say thank you again to the organizers and NIMS and the audience.